Okay, maybe we will start the guest lecture. Ya, Bapak Ibu, yeah. Okay. Hello everyone, and welcome to this session guest lecture presented by Study Program of Bioprocess Engineering, Faculty of Agricultural Technology, Universitas Brawijaya. I am Ingrid Kresna Maharsi. I will be hosting and moderating this session. And today's topic is about ion exchange membrane development and application for electrochemical energy. First of all, we are going to start the event with a welcome speech. Please be invited, Dr. Wahyunanto Agung Nugroho, Head of Bioprocess Engineering Laboratory, Universitas Brawijaya.
Okay, thank you, Bu Ingrid. Hello, everyone. Good afternoon and welcome. And thank you for joining us today. And we are excited to have Dr. Ramato here. He is one of the experts in membrane technology. And today we have such a great opportunity that we can learn from him about membrane technology, especially in the ion exchange membrane. It is for electrochemical energy system. Welcome, Dr. Ramato, and in advance, I need to say thank you for coming in this lecture and to give a lecture. And we're supposed to have at least about 40 students, and we already have 63 students today. And most of the students, they are from Dr. Yusuf's class. They doing the course in membrane technology. So it is like a one semester course in membrane technology. So the student will gain quite good knowledge in membrane technology, and also they have the live practice as well. But unfortunately, to be honest, we don't have such sufficient knowledge in ion exchange membrane. So if today we are very delighted that you gave this lecture on ion exchange membrane. And for students, please open your camera, and we actually invite you if you probably have any questions. Please don't hesitate to ask Dr. Ramato. And if you are probably excited to do any research on ion exchange membrane with Dr. Ramato, you may contact him as well. So probably if you are excited to do the research in Italy, probably for your PhD, probably, and he probably will welcome you in Italy as well. It is he is actually from. Is it okay, Dr. Ramato?
Ethiopia.
All right, it's open. Yeah,
Ethiopia.
Yeah, in Ethiopia. Oh, you're in Ethiopia now? No.
No, I'm originally from Ethiopia, but I'm in Italy now. I'm working in Italy.
But you're working in Italy now?
Yes, yeah.
All right, so yeah. He's from University of
Calabria.
Yeah, Calabria. It's such a nice city in south of Italy, and if some of you probably interested on doing the research in Italy with Dr. Ramato, you can contact him, and for the funding, you can probably apply for Indonesian government scholarship later if you are really interested in that. So I don't want to make this speech too long, and I cannot wait for the lecture as well. So I return it to Ingrid Kresna to be the moderator of this lecture.
Thank you, Dr. Wahyu, for the welcoming speech. For dear participants, before we continue the session, please let me to tell a quick notes for this session. Yeah, this session will be divided into two sessions. The first one is a lecture delivered by Dr. Ramato, around 45 to 50 minutes. And then it will be followed by the discussion section. And then for participants who will ask the questions, please, you can directly raising your hand, or you can type your question in the chat box. I will read your questions. And the last but not the least, please turn your camera on, yeah, and please stay in the Zoom, yeah. And then for the next, I would like to introduce for the today's speaker, Dr. Ramato Tufa. Yeah, I will read your profile first. Dr. Ramato Tufa was an awardee in Erasmus Mundus, both in master and doctorate degrees. He is in joint master at Gdańsk University Technology, Poland, and University of Barcelona, Spain, and then continued in joint doctorate in 3 universities, in University of Calabria, University of Twente, and UCT Prague. And subsequently, he joined University of Calabria in collaboration with Institute of Membrane Technology of the National Research Council as postdoctoral researcher. His expertise is material and process development for renewable energy conversion and storage system, including reverse electrodialysis, water electrodialysis, and batteries. And Dr. Ramato, you have around 45 to 50 minutes to present. Please, the time is yours.
Perfect. Thank you. First of all, I would like to thank you for the kind introduction and also for inviting me to give this lecture. In fact, we have been planning with Yusuf this lecture very long time ago, but due to my situations, it has been postponed and came to this time. Even recently, I moved from Denmark to Italy for job reasons, and my time was a bit tight, and it was not so easy to compile my things. Still, you can see I'm not very well set because you can see that my camera is not very clear. But next time I will just hold this in a very clear way. As I'm settling now in Italy. We plan to do a series of lectures, if possible, and this will be the first lecture, and our lecture will be, as introduced, it will be on ion exchange membrane development and applications for electrochemical energy systems. So, in this session, in today's session, depending on the time, we will try to cover to understand the fundamentals of ion exchange membranes, how we can characterize them, some unique designs of this type of membranes, and also the applications that we will not see all the applications, but today I will show you one of the applications which in a technology which I have been using during my PhD session. So an introduction have been given about me. My background is chemistry and my PhD is chemical engineering, or it was an Erasmus program which is Erasmus Mundus Doctorate in Membrane Engineering. So it's as you can see, I have traveled in many European countries for research and for study purposes. Recently I was in Denmark. Now I moved to Calabria, where I plan also to continue my research. So Calabria is located in the south of Italy. It's very well characterized by its natural beauty, as you can see. And I'm happy, as previously said, I'm happy to welcome you all if you'd like to visit Calabria for research or for any other purposes. To this beautiful region. The University of Calabria is also a very big university. As you can see, it hosts more than 3,500 students, 800 teaching and research staff. The university is, you can see it's like a well-aligned. There's a very long bridge about 2 kilometers, about 800 meters long, and the different departments, the different buildings, as you see, are in line. And it looks actually nice also. So, I'm at the Department of Environmental Engineering. And the Department of Environmental Engineering is focused on research in different research, including membranes for water and for energy as well. So me, I'm more focused on the applications for the energy purpose. So I will not take much time for introducing a lot about stuff. So I will directly go to to what we plan to understand today. So today, as I understand, the students that are here today have a little background on membrane. So it means that you know the maybe constituents of membranes, how membranes, the types of membranes, and you might also know the structure of membranes, the applications in some fields. So yeah, so it means I will just cover one part of the membranes, which is the ion exchange membranes. And in this, after this lecture, I hope you'll get an understanding on what are the ion exchange membranes, how do they function, and also their structure and how we can characterize the ion exchange membranes and what are the applications. So I will not talk all the applications, but I will just mention one specific application for today, depending on the time. So if you have a question, you can also ask me in between. And also I'm happy to discuss and share with you while I'm talking some things between all of us. So feel free to stop me and ask when you have a question. So it is nice that you have a little background on membranes, since you are from membrane classes. Membranes, because sometimes when I talk to people, when I say membrane, so they think that, okay, there are biological membranes, there are other natural membranes, but the membranes that we talk in the chemistry class are not those membranes. So we are just talking about artificial membranes or man-made membranes. In particular, in today's lecture, we are going to talk about ion exchange membranes. So apart from ion exchange membranes, I hope you have been looking at some other types of membranes. Is there anyone who can mention me what kind of membranes you have been dealing in the class? The type of membranes that you know, or yeah.
Any students can answer,
Yeah.
maybe?
Any, like these ion exchange membranes are one type of membranes. So what are the other types of membranes that you know? So in case it's not clear, the ion exchange membranes are one type of membranes. So generally, let's say we can classify membranes into two: the organic and polymeric and inorganic membranes. And the polymeric membranes can also be further divided into porous, dense, and so on. So the polymeric membranes, so the ion exchange membranes, we can say polymeric membranes. They can come in a class of polymeric membranes. They can also be actually a composite. So sometimes you might have some inorganic materials inside, but in a broad sense, we can say they are polymeric membranes, which come under the class of polymeric membranes. On the other side, you have inorganic membranes, which can be ceramic, glass, and so on. So I'm quite sure in the class, maybe you have had these membranes for reverse osmosis or other separation systems, which are also polymeric membranes as well. So as ion exchange membranes are polymeric membranes, but specifically what these membranes are that we are going to see today and how we make them. These membranes have been introduced a long time ago, so just more than 15 years that these membranes are known for. And the first application was in electrodialysis, which is also a well-known technology in many industries. let's go directly to ion exchange membranes. So have you ever heard about ion exchange membranes? Anybody knows about ion exchange membranes? So what are the ion exchange membranes? So if you have not heard in your class what the ion exchange membranes are, or if you don't know what the ion exchange membranes are so far, as I said before, they come under polymeric membranes, and the ion exchange membranes in particular allows you for a separation. Membranes in general are used for a separation, but these ion exchange membranes, as you see from the name, they are ion exchange, so they separate ions. So it means that the ion exchange membranes do not separate all ions. So because they are charged, they separate one type of ion. So if they separate cations, if they separate anions, so we give them a name. So we say cation exchange membrane, anion exchange membrane. In this picture examples that you see, if you put this type of membranes in solution, let's say containing sodium chloride, you have sodium, you have chlorine. So as you can see, chlorine cannot be transported, but sodium can go inside. So it means that the charge, these charged materials or these charged membranes or ion exchange membranes allows you to selectively separate one type of ion. So in this case, a cation exchange membrane, because they transport cations. So it is the fundamentals of understanding or the research on ion exchange membranes, once you know what these membranes are, you need to understand what the structure is. So as I said, they come under polymeric membranes. So the polymeric membranes with a structure where you can see here constituted from different components. So we can say, we can group the components into, let's say, different terminologies. All right, as I said, if you put your ion exchange membrane in solution, so there are different phenomena, different chemistries that are happening. So so the membrane or the sheets which I will show you later what it looks like, will have a backbone. So there is a backbone which constitutes the membrane. So that is what you call the polymer matrix or the backbone, as you see in this structure. And then I said these are charged membranes. So they have charges. They have negative charges, they have positive charges. So if they have a positive charge, they will selectively transport negative ions. So we call them the anion exchange membranes. So if they have a positive functional groups, if they have a negative functional groups, they selectively transport cations. So we call it cation exchange membranes. So these groups that I'm talking about, the functional groups are the groups that provide the ions, the charges, or the functionalities. So they are called fixed charge, or it's called the functional group attached to the polymer matrix. The ions, I'm talking about the ions are transported. One ion is transported, one ion is blocked. So so it is very important in this field to know what counter ion is, what co-ion is. So the counter ion is the ion that is transported. So for example, I said in the cation exchange membrane, cations are transported. So the cation is the counter ion, and the chlorine is blocked, or the anion is blocked. So that is co-ion. The one which is not transported is called co-ion, because it has the same functionality or the same charge as the fixed charge groups. So it is very nice to understand these terminologies when we talk about the ion exchange membranes. So you need to, so the backbone, there's a backbone, and then there is a functional group. So the functional group can be either positive or negative, depending on the type of membrane. If it is positive, we call it anion exchange membrane because it transports only anions. If it is negative, we call it cation exchange membrane because it transports only positive ions. If it is if the functional group is negative. So in other way of presentation, we can show it like this. So the functional group, so the polymer backbone, you can see here, like the backbone can have different structures. So the research in the field, in this field, just goes on by playing with the structure of the backbone, as you see, and where you put also the functionalities. So this functional group, the negative functional group in this case. So you can put it either in this backbone or in the side chain, okay? So if you put it on the side chain and if you put it on the backbone, these are two different membranes. They have very different properties and they behave different in different applications. So in principle, the design or the formation of this type of membranes, as you can see, is made by changing the composition of the polymer backbone, or if you have the side chain and where you put the functionalities either in the top or in the polymer backbone. So so it is very important. Changing the structure of this backbone and the side chain completely changes the properties of the membranes. So that's what we basically look into. And we also change the type of these functional groups. So these functional groups can be carboxylic functional group, sulfonic functional group, amine functional groups, and so on. So sorry that I didn't show you here, but most of the time, for example, in the cation, when we have these negative functional groups, they are sulfonic groups. And when you have a positive functional group, they are amine groups. So you can just introduce amine functionalities to form anion exchange membranes, or you can put sulfonic functionalities to form cation exchange membranes. I will discuss this later. I will show you in my later slides. Yeah, here again, a review of the different types of membranes. So what I want you to keep in mind is only the most important types of the ion exchange membranes, the cation exchange membranes and the anion exchange membranes. There are also other different varieties of ion exchange membranes, the bipolar membranes, where you can put the two ion exchange membranes together, as you can see. So, and then you can also use them as a membrane that also have a different characteristics. There are also other types of ion exchange membranes which are least considered, like amphoteric ion exchange membranes, mosaic ion exchange membranes. But these are the most important ones are the cation exchange membranes and the anion exchange membranes that we are going to deal with today. So as I said before, the backbone can be a hydrocarbon. It can also be a perfluorinated material. It can also be inorganic material. It can also be composite of organic and inorganic. So by changing the backbone composition, you can still control the properties of the ion exchange membranes. So hydrocarbons, perfluorinated, in some membranes, if you use the perfluorinated backbones, you have better properties and better performance. But the perfluorinated type of membranes are quite expensive to produce. So, for example, if you see Nafion is a perfluorinated membrane with a backbone, and it's quite expensive compared to the other membranes which are just made simply from hydrocarbons. So, yeah, inorganic membranes are also sometimes important in some aspects. They perform well and better. Composite membranes, where you have organic, inorganic materials all together. So that's how we change the structure of the membranes and how we investigate the variation in the properties for the different applications. Mostly in my case, we did with hydrocarbon membranes because they are very cheaper and also they are very easy to produce. So if somebody asks a question of, let's say, how I tried to show you previously how we can classify ion exchange membranes. So I said, depending on their functionalities, we can classify them as cation exchange membranes, anion exchange membranes, bipolar membranes, and so on. But two most important, anion and cation exchange membranes. But also, depending on the structure, we can also classify the ion exchange membranes. For example, the homogeneous membranes and heterogeneous ion exchange membranes. What is the difference between the homogeneous and heterogeneous ion exchange membranes? It is also very important to understand this because for some applications, the homogeneous membranes are important. For others, the heterogeneous ion exchange membranes are important. So the homogeneous ion exchange membranes are the membranes where the fixed charge groups that I showed you previously, that gives the functionality to the membrane, is evenly distributed in the polymer structure. So it means that there is a one phase between the polymer backbone and the charge group. So it's like homogeneous. But if you go to the heterogeneous type of membranes, the ion exchange groups are just distributed in the polymer backbone in certain domains. So the composition changes from place to place inside the membrane, and so you can say, and the functionalities are not directly creating one phase with the polymer backbone, but they are creating different phases. So yeah, for example, if you have a polymer backbone and you have a resin, so there is so they are separated and they form two different phases. And that is what we call heterogeneous membranes. Generally, the homogeneous membranes are very conductive. So now if I say to you conductive or then you need to also know what are the properties of ion exchange membranes, but we will come to that later. So the resistance of this kind of membranes is very low, the homogeneous one. But the heterogeneous ones are less conductive or very high resistance, but they are mechanically strong. So you can use them, let's say, in a very, let's say, under a quite high temperature, or you can use them in a quite harsh environment. They are quite stable and also quite, but they have a very low resistance, very high resistance. So depending on which type of application you would like, you can choose the homogeneous membranes. As I showed you before, we have in the structure of the membranes, let's say here in the homogeneous membranes, we have the polymer backbone, the functional groups, and so on. So, but how do they look like? How do the ions are transported in the membrane, or what does the structure looks like in the sense of transporting the ions? So there are different models to describe this. So it is not really very clear how the ions are transported really in the membrane. So, but there are different theories, and the most accepted one is that in the membrane we have a gel phase, okay, and then we have a fixed charge groups. So that gel phase is a phase containing the fixed charge groups, and there are also channels inside where the ions freely move in the channel. So there is a gel-like structure where the fixed charge groups are in, and there are also channels within between the polymer backbones where the ions are transported along with the water. So here, what you see is the structure, the anticipated structure of the ion exchange membrane, where you have the functional groups and the ions, free moving ions immobilized in the channel. And sometimes here you see the brown structure on the very left side, this brown structure, which is just, let me use pointer. Yeah, so this brown structure here is like a reinforcement, where you add the reinforcement in order to just give some mechanical strength for your membranes. Yeah, it's most of the membranes that we use for our application are homogeneous membranes because they have a very low resistance compared to the heterogeneous membranes. So how do we form the ion exchange membranes? How do we prepare the ion exchange membranes? So have you tried to, did you have some practical experience in the lab to prepare membranes? Can anybody tell me how you can prepare membranes in the lab, or have you done some practical stuff in preparing membranes in the lab in a very short course? If you have been dealing, for example, with reverse osmosis membrane or other types of membranes, how you prepare in the lab, or the methods that you use to prepare membranes in the lab. If you did some practical experiments or something in the lab, is there anybody who can tell me how we can prepare some membranes or a method to prepare a membrane in the lab? It can be any type of membrane. If somebody can tell me or would like to tell us, yeah.
For the student, you can turn on the microphone for answering.
If somebody would like to tell us how, if somebody who have experience in preparing membranes, and if you would like to tell us his experience in how we can prepare membranes in the lab, it can be RO and so on. Then if you don't have, I have also a video to show you later, and after some minutes. Anybody? Okay. So yeah, let's say today we are talking about ion exchange membranes, but also for the other type of membranes, which I told you that you can use it for other applications, which are not charged membranes. For example, for water purification, some of the methods are the same, but there are a slight difference. So I will just mention some particular methodologies to make this type of membranes. For example, some general methods or unique methods to prepare the ion exchange membranes that we follow. So the first one is like polymerization of monomers. So you have a certain monomer. So I told you previously that we have a backbone and we also have a functional group. So these are the two questions. So if you have a base material which contains both the functional group and the backbone, then you can, in a certain way, you can polymerize it and form a very thin film, or you can form a certain structural material. So the first one is like polymerization. Polymerization of a base material containing both the backbone with the neutral backbone and also the functional groups, which can be cationic or anionic functional group, as I have discussed before. So the other way is you can introduce the functional group to the backbone, so by a certain chemistry. So you can have a mixture of neutral polymers with the polymers containing the functional group. So you have two different base materials. You can put them together in a certain under controlled chemical conditions. You can just form the ion exchange membranes by a chemical reaction, an organic reaction, or whatever kind of chemistry you use for the compounds that you choose. So that's based on the preparation of block polymers or block polymers, which constitute the backbone of the ion exchange membrane groups. So, well, these are the two common ways where you can prepare your ion exchange membranes, either from a base material containing functional groups and the backbone together and polymerize, or you have the backbone and the functional group separate, put them in a certain chemical condition and then form the ion exchange membrane. Okay. The other way is also like functionalization of the polymer again through the chemical reaction, where you can introduce the functional groups by different methods. For example, by grafting, by plasma, or by chemical reaction. So you can have a polymer, and then you can have, let's say, a polymer with a backbone. Then you can directly introduce the functional group into the backbone by a certain chemical reaction, or by grafting. This plasma grafting, or different other methods. This is the most common method to just functionalize the membranes with the polymer backbone with the functional groups that you want. So the functional group can be either cation or anion and so on. So the functional group introduced before or after film formation. So you can, so when I say film, you have the sheet of membrane. So you can first introduce the functional group into the backbone and then cast to form a sheet, or you can also cast the backbone first and then introduce the functional group. So we work in both ways, depending on the type of membranes you would like to form. I will show you one video because if you don't have any practical experience in the lab in preparing or casting the membrane. So there are different ways of forming the membrane. So one way is by casting. Let's say I would say general casting. So there are different ways of casting also. So by phase inversion, or just solution casting from a solution, or and so on. This video that I show you will be by casting from a solution. So from a solvent using a casting machine. Let's just try to have, I need to open this video. Okay, perfect. Do you hear the voice?
Not yet, Dr. Ramato.
Can we turn?
I don't know what the reason is, but there was
probably you need to change the setting from your Zoom.
Yeah, let's try to change the setting in the video. No,
I think when you want to share the screen, there is no option, and on the bottom left, there is an option that you probably can on your audio.
Okay, on the
sharing. Before you're sharing, yeah. So you can turn off your screen and try to share again. And on the bottom left of your screen before you share the screen. So you click the share screen, then on the bottom left, there is an option that you can click whether you want to share the audio or not.
Let's start again, okay? If not, it's not important. So I can just
give the narration.
It was a music. So
all right.
I can also explain I mean, I can talk. So once they see the video, there is also subtitles. Here I can, I see on the left side, audio. Okay, optimize video clip. Now, which screen do you see my slide now, or?
Yeah, we can see your slide, but I'm not sure if we can hear the audio.
Yeah, I think
it's okay. Yeah,
you cannot hear my audio, no? I think I also cannot hear. So I I will just yeah, there is a subtitle, but I will just also explain. So there is a written subtitle. You can just, I will fix that next time. So you see in this video, we have the casting machine where we can form our membranes from a solution. So generally there is a casting machine that you can purchase from a certain suppliers. And this is the knife blade or the doctor blade where you can change the size to control the thickness of your membrane that you form. So you can, so you can use different type of knives, and you can set your machine to a certain speed that the cast moves, faster or slower, depending on how you want to move it. It's not very complicated. So it's just simply you have the knife, as you see, the casting speed. You can see how, so in the knife that I showed you before, you put your polymer solution and then it just moves in. So you can cast your membranes on the glass. Usually we use the glass plates, the one on the bottom. All right, so this shows you how to adjust the casting speed and so on. Back now, let's see. Yes, so this is the polymer solution, right? So as I said before, you can, these polymers can be either with a functional group or without functional group. So they can be simply a neutral polymers or the charged, can also be charged. So depending on what you want to do. But this is how you prepare your solution first, before you just cast your membranes on the solution. So so the thickness is the thickness of the membrane that you want. You can choose based on the knife. So that shows you how to install, but that's not very complicated. So, and once you have it like this, you can pour it into a solution. You can pour into the just simply pour it. So that's a polymer solution. You have the backbone that you dissolve it in a certain solvent, and then you try to cast it. So, all right, and so it is very important that you make sure that the level is like uniform in the when you fill in the casting knife. And also it is very important that the speed, control the speed, because it also determines how uniform the thickness will be. So that's why we use a very flat glass. So you can see that it just forms a film on the glass plates that you have. All right. So you just cast your polymer solutions. You take it out, okay, as it is, and put it in a water or in a salt solution. In a water or a salt solution for some minutes, and then you will find this type of material. So this one is called phase inversion, because immediately, as soon as when you put your film in the water, there is exchange of solvent between the water and the organic solvent, and then immediately you form this kind of strong, mechanically strong polymeric membrane where the solvent exchange, and that's what we call phase inversion. We call it phase inversion. So this method is a phase inversion. So here your membrane is ready now. So you can see immediately when you put it in the water, it's coming out. So it is ready. So you can use it. This method that you saw now, when you cast your membrane and put it in a water solution, you form a porous membrane. So if you scan this membrane and see under microscope, they are porous membranes. So you can, so they are not dense membranes. So our membranes can be porous or dense, but mostly we use dense membranes. So you can densify these membranes in further step and so on. The ones that I showed you in this video is phase inversion, but you can also use you can just cast it and then put it in an oven and dry the solvent as well. So if you follow that kind of method, then you form a very dense membrane which doesn't have pore inside. If the method that I showed you now will give you a porous membrane, which is also called a phase inversion. So the most important point for me to you here to understand is that the most common way of forming these membranes that you saw before is by casting. So casting from a solution is the most common way to produce this type of membranes. How many minutes do I have now in order to accelerate my slides?
Around 10 minutes.
10 minutes, yeah. So I think we will proceed in another lecture, but I will just quickly cover some of the properties of the membranes in this last 10 minutes, and the rest, as I promised, we will hold another series of lecture in another time. So in our previous, if you have a question, feel free to ask me, okay? Or we have a question and answer session later. In the first part of my lecture, I think it's clear what the ion exchange membranes are, how they work, and what is their functions, and what are the different types of ion exchange membranes, as we have discussed. So I will not take much time now, but in the last minutes, I will quickly show you what are the most important properties of the ion exchange membranes. Because if you previously I showed you how we can cast and make the membrane, but how do you know if that membrane is good or bad? So then you need to characterize it. So how do we characterize the ion exchange membranes? So in order to, before characterizing, or when you characterize, you need to know what are the properties of the ion exchange membranes. The very important and the very common properties of the ion exchange membranes are the electrical resistance, the permeability, ion exchange capacity, swelling degree, fixed charge density, and so on. These are the different, the most common properties of the ion exchange membranes, where in which you can characterize them to just say, okay, this one is good, this one is bad. The electrical resistance is how well the ion exchange membranes transport ions. Previously, I have shown you homogeneous and heterogeneous membranes. The homogeneous one, I said, have very low electrical resistance. What does that mean? So it means these membranes transport ions quite fast, very fast. So depending on the application, that has a very important advantage. So because the productivity can depend on how fast the ions are moving through the polymer backbone. The permeability is another parameter which has to do with the transport, but permeability is related to how well the ions transport one ion and exclude the other. Because I said anion exchange membranes, for example, transport anions and they exclude cations. But how well do they really exclude cations? And that's how you measure with the permeability. Because if your membrane is passing in both chlorine and sodium, then it is not an ion. It is just not really an ion selective membrane. So it should selectively pass only one type of ion. So if it is cation exchange membrane, only sodium. So how well will a cation exchange membrane retain chlorine, for example, without passing? That is how you describe the permeability. And this permeability and the electrical resistance depends on the ion exchange capacity. What is the ion exchange capacity? The ion exchange capacity is how much the functional group is present in the membrane. Because previously we said the functional group, which is positive or negative, allows you to transport, to control the ion transport. And how well how much the functional group is inside the membrane is what you call the ion exchange capacity. The swelling degree is also very important. This is a very important, the swelling degree, because you put the membranes in the water, how much water do they uptake, they swell when you put them in the water? Because that is very important. Because the ions are not transported in a dry membrane, right? So we need to have a solvent or a certain amount of swelling so that the ions pass through the polymeric chain, transport through the membrane. So the swelling is also very important. So how much water do the membranes uptake or gain when you put them in the water? Here I put the different formulas. You can study them because I will send you later the sources. Fixed charge density is just a little bit different from ion exchange capacity, but it is the ion exchange capacity divided by the swelling degree. So which means the ion exchange capacity of the membrane in a dry, like the dry weight, in a dry per dry weight. So the fixed charge density also explains, also helps you to understand how the membranes behave, for example, in a very highly concentrated salt solution or in a very low salt solution. So depending on how they swell and how they shrink and so on. Because, for example, if you put a certain membrane, for example, in 5 molar sodium chloride and in 1 molar sodium chloride, it really behaves very different. So that depends on the fixed charge groups. So, for example, if you put it in 5 molar sodium chloride, the perm selectivity drops down, it dies. So it means because the concentration of the ion is really very high, so it transports all the ions. So it means the perm selectivity will not be very good. So that the fixed charge density helps you to understand these kind of things. It is very important to see these characteristics, for example, in commercial membranes. Here, what I'm showing is some of the properties of the commercial membranes. The different properties that I showed you before. So the thickness, resistance, and so on. So in the market, there are a lot of ion exchange membranes that you can use it for the technologies that you want. Yeah, for example, there is a company providing Ralex membranes. This company is in Czech Republic, and one of my colleagues just working there. But we don't use this kind of membrane so much because these membranes, they are very thick. You see their thickness, like they are 764 microns. So they have a very large resistance, and it's just not useful, at least for my technology, which is a reverse phase technology, where I need a very low resistance membranes. On the other hand, there are, for example, Fumaset membranes. These are very thin membranes. You can see even 34. You can find them in 34 micrometer thickness. And this kind of membranes, if they are very thin, you can see they have a very low resistance. Let's see how these properties are interconnected. You can see here, this is one of my colleagues in University of Twente who characterized the commercial membranes and made this plot. So you can see, like, for example, when the charge density increases for some of the membranes, the perm selectivity also increases, right? So you really find a membrane with a very low charge density and low perm selectivity. So most of the membranes you can see are like, when you go up with the charge density, the perm selectivity improves somehow. The resistance and the perm selectivity, how do they relate? So the very challenging the very tricky thing is that you cannot improve the resistance and the perm selectivity together. So when you reduce the resistance, the perm selectivity falls for most of the membrane. You see, so low resistance, perm selectivity is down. Very high resistance, perm selectivity is good. So if you are able to make membranes with a very high perm selectivity and very low resistance, like in this region, you are really excellent. So you see, like, it's very challenging to make membranes in this region. Very low resistance and very high perm selectivity. That is one of our challenge in our research, at least in the technologies that I am using, which I will show you, I think, in another lecture. Okay, the last slide, I think our time is over. So we are talking about how we can characterize the membrane and the properties. So here you can see how the different membrane properties are interlinked. So in our research, our main challenge is this: how we can, if you want to improve one parameter, the other goes down. If you improve the other one, the other goes up. So that is the challenge we have. And for example, if you have the ion exchange capacity, which is very, let's say, low or high, you see, it has a positive relation with the charge density. So the charge density, if you have very low or high, it has a direct correlation with the perm selectivity. So which means that if you increase charge density, the perm selectivity increases. If you reduce charge density, the perm selectivity reduces. The mechanical strength and the resistance. If you want to improve the mechanical strength, you need to make the membrane quite thicker. And if you make it quite thick, the resistance drops down. So, and reinforcement also, which makes the mechanical strength quite strong. And you see the percent reinforcement have a negative correlation with area resistance, because if you reinforce your membrane, the resistance will go down. So it means the transport of ions are reduced. Mechanical strength, resistance. Does it have a positive correlation? I will just leave this for you. Because how you improve the mechanical strength is basically by making it quite thicker. So if you make it thick, the resistance should reduce. I think here is positive, is not well correlated. So the percent cross-link also with, okay, if you want to improve the mechanical strength, you need to increase the percent cross-linking. Cross-linking is as I didn't show you, but cross-linking is also one type of variation of the structure, just with by putting some type of polymers inside the membrane. And by increasing the cross-linking, you can increase the mechanical strength. By increasing the cross-linking, you reduce the swelling. If you reduce the swelling, you increase the charge density. But if you reduce the swelling, the ion exchange capacity also gets reduced, because they have direct correlation. So that is the tricky part. So these different properties are very difficult to control in the lab, and that is basically what we deal with when we make membranes for the different applications and so on. And that is, as I told you before, it's a very difficult challenge in ion exchange membrane. For at least for our purpose, is the two parameters, the two most important, the perm selectivity and resistance, are very difficult to improve, both of them together. So that is very, very difficult. It is very difficult to make the membrane with a very high perm selectivity and very low resistance. And yeah, so in principle, that is where the challenge is. So in the next lecture, I will just talk more about the characterization, physical characterization, and impedance measurements, and also the let's say the impedance, electrochemical impedance, and some of the unique designs like monovalent selective membranes, how we can make monovalent selective membranes, how we can characterize them physically. I will give you some examples. And so for the application, I will deal with one of the technology which I'm using, which is a blue energy. So how it works, what's the blue energy, and how we extract form energy from seawater, river water. And for these purposes, we use ion exchange membranes. So I will discuss the theoretical thermodynamics and so on of the river surfaces technology, which is a salinity gradient technology, and so on. So I think, yeah. So I will deal this with another session of our lecture. I think I will end the first lecture here, and I would like to thank you very much for listening. And I'm very happy to welcome you for your questions. And I will say Tarima Kasi. Yeah. And feel free to contact me for now. Please feel free to contact me in my private mail. After some time, I will have my institutional mail. And I will also share the institutional mail with you. Yeah, if you would like to collaborate with me in terms of project or in terms of application for your PhD and so on, feel free to contact me anytime. Our group here, the University of Calabria, we also collaborate with the Institute on Membrane Science and Technology, which is an Italian national research institute. Maybe next time I will also give you a brief introduction about that. So the group is a leading group in the field of membranes in the world. So there are very nice people, very great people in this Institute of Membrane Science and Technology, which closely works with our department. Perhaps next time I will share you this information. And for now, please feel free to contact me regarding your master's thesis if you would like to do some internship on ion exchange membranes with us for different applications. And also PhD, if you would like to look into PhD opportunities. Yeah, I will also forward it to Yusuf so that he can share it with you. I'm just, I would just end my talk today here, and I'm happy to discuss with you if there is some unclarities and some questions. Thank you very much for listening.
Thank you very much, Dr. Ramato, for the very detailed fundamental of ion exchange and for welcoming us for collaborating with you, yeah, for the research. And for the next session is a question and answer for the dear participant. You can directly ask by turn on your microphone, or you can type your question in the chat box. I will read your questions. So it is one question, yeah, from Alfonsina Abad Amelenan. I will deliver the question for Dr. Ramato. Yeah.
Yeah. Yes.
Yeah. Thank you for your very interesting presentation. May I know how do you manage to get good values per perm selectivity in your experiment? Also, I'm a bit curious about the electric saturation of the ion exchange membrane after it is full use or saturated. Can it be regenerated or to use it again? Yeah.
Yeah. Okay. Interesting. The first question is, how do we improve the perm selectivity? And the second question is, I think, how do we once we use the ion exchange membrane, can we regenerate it? Yeah, let me first of all, so before answering how do we improve the perm selectivity, then it's very important to understand the perm selectivity itself. So as I said before, the perm selectivity is the property of the membrane. So we say it's selective membranes, all right? The ion exchange membranes are selective membranes, so they need to exclude one type of ions. So if I talk about cation exchange membranes, they need to exclude, maybe I will show you here, you see. So these membranes, this is from different Okay, maybe instead of this, let me show you this one. So here you can see that sodium is passing and chlorine is blocked. So the membrane is there, and the permeselectivity is how well the sodium is blocked. So this is the cation exchange membrane because it is transporting sodium. Sodium is a cation, so it is a cation exchange membrane. So the permeselectivity tells you if you have, for example, 95% permeselectivity, that is a very good permeselectivity. So it means that it just excludes about 95%, let's say, of sodium chloride, of chlorine in the solution. So how do we improve? So the first, let's say it's a little bit tricky. The functional groups are important. So the functional groups, because if you have a very, let's say, low fixed ion exchange capacity, as I told you before, here, so the permeselectivity is here, all right? So we have the charge density. So the charge density is the ion exchange capacity divided by the swelling degree. So it all relates to the ion exchange capacity. So if you increase the ion exchange capacity of the membrane, you improve the permeselectivity. So you need to, so the critical parameter, I would say, is the amount of ion exchange functional group you have in your membrane. So it's actually the ion exchange capacity should not be also very high. If you do like that, it will swell very much, too much, and then it dissolves also in the solution. So there is actually optimal ion exchange capacity. The membranes which have a very high ion exchange capacity in the water solution, they dissolve. So, but so there is an optimal ion exchange capacity where you have a good permeselectivity, and mostly you can improve the permeselectivity by controlling the amount of ion exchange capacity in the membrane. That is one thing. There is also another external parameters that influence the ion exchange, the permeselectivity. For example, the concentration of the external solution. If you are putting it in brine and if you are putting it in let's say in a low concentrated solution, 0.5 molar, it's not behaving the same. So if you put it in 5 molar solution or in brine, the permeselectivity dies. So it is also influenced by composition of the external solution, but you can improve the permeselectivity by controlling the ion exchange capacity mostly. I would not say the polymer backbone. So if some backbones, maybe depending on the side chains, can also alter the permeselectivity, but most important, in my opinion, is the ion exchange capacity. So that's one thing. Of course, you need to be careful on how much ion exchange capacity you put, because if you put, as I said, if you put too much ion exchange capacity, then it dies. It just dissolves. It will be soluble it will not function well. It swells too much, it dissolves in solution. Yeah, so that is one thing. So the second question, where can we, how does the ions transport, the electrical transport, and then can they be regenerated? So this is one of the problems we have in our research also, for when we apply ion exchange membranes in a certain solution. For example, when we use the membranes for hydrogen production in water splitting, we perform this operation in potassium hydroxide, in a very highly concentrated potassium hydroxide solution. So if you put your membranes in potassium hydroxide for several days, the functional group will degrade. The functional group slowly dies, so they will disappear from the membrane. So which means that when you tell me like, can we regenerate, reuse, this is about the lifetime of the membrane, in my understanding. So you can, once you use it, for example, if you put it in sodium chloride, if you put a cation exchange membrane in sodium chloride, it will be in sodium form because sodium will be in the membrane. So you can take it out and use it again. It will still transport sodium. It's no problem. But the problem is when you use it again and again, the functional groups slowly degrade with time. They depending on which solution you put them. If you are using it in water, you can use it for a really long time. Or if you are using it in a neutral solution, you can use it for a very long time because the functional group are not affected easily. But if you put it in potassium hydroxide, as in the case of water electrolysis, where you produce hydrogen, that is another thing because the functional groups start to degrade immediately and you cannot use the membrane and again because the functionality dies immediately. So that is one of the challenge also we have to make. We call those kind of membranes stable membranes. So stable membranes that, okay, you operate them, you can use them for 100 years or not 100 years is too much, but maybe 2 years, 3 years. You can use them in industry. So those are very stable membranes. But the other membranes which are not stable, you need to change them with time. And also this has to do with the polymer backbone because the backbone also degrades and also the functionality degrades as well. So, your second question has to do with the stability of the membrane, in my understanding. So the stability is really influenced by the amount of functional group, by the type of functional group that you have inside the membrane. So one of the research is in for example, when we use anion exchange membrane in the water electrolysis to produce hydrogen, we just strive to make membranes which are really very stable in potassium hydroxide because potassium hydroxide is very aggressive and the membrane immediately dies. If you operate it in 1 week or 2 weeks, it just dies. So you can still reuse them, but it depends on what type of membrane you have and how stable it is, depending on its structure and functionality.
Okay, for Alfonsina, is it clear for you? Okay. Okay, maybe we will move to the next question, Dr. Ramato. And this question is from Marlene Andriani. Yeah. As I know, ion exchange membrane can be applied to seawater desalination with electrodialysis process. Is there any application of ion exchange membrane that we can find in our daily life, or there is simple application of ion exchange membrane?
Okay, so actually, this is also a good question, but a bit related to what we plan to do in the next, because next time we are planning to discuss about the application of the ion exchange membranes. So in order to, but I can give a highlight. So it is nice that you have did in your class on electrodialysis, that you know that ion exchange membranes are used in electrodialysis. In fact, that is the first technology where the ion exchange membranes are used. And you know the electrodialysis is used in different in industries for different applications, including food and also water purification and so on. So in our to your question, in our daily life, the ion exchange membranes, apart from this electrodialysis, there are many different other technologies that the ion exchange membranes are used. But I'm not mentioning all those technologies. 5 minutes ago, I said, for example, to produce hydrogen. So you know that we have energy crisis now, and hydrogen production is one of the main lines. So we can produce hydrogen in different methods, and one of the methods is by splitting the water into oxygen and hydrogen. And we can do this by ion exchange membranes also. So one of the application of the ion exchange membranes is in water electrolysis, where we want to produce hydrogen. So that is one of the key research, especially nowadays with this war we have and so on, where we strive to avoid fossil fuel and all these things. That is one important application in our daily life. With desalination is also very important. So there's the desalination part to produce pure water for our daily consumption. Not only daily consumption, but also for some application. For example, you need an ultra pure water in some in lab works or even in some medical facilities or other places. You need there is a time where you need ultra pure water. So the ultra pure water, you can, one way to produce is, for example, by electrodeionization. The electrodeionization doesn't directly use ion exchange membrane, but the principle is like ion exchange because we have a resin and it works with the ion exchange. There are there are different applications where we use the ion exchange membranes. Let's say in not directly in our daily life, but for the to make the things that are used in our for our daily life, energy. So as I told you, hydrogen production is one part in water electrolysis, and also the water, so the electrolysis to produce pure water. Yeah, there are other applications, but they are not very well let's say into the market or into the real application. For example, if I tell you that we can make some raw materials to make plastics, for example, ethylene. Okay, from carbon dioxide you can produce ethylene. Ethylene is used in many industries to make plastics and other things, and you can use ion exchange membrane to convert carbon dioxide into ethylene by a certain reactor. You have a membrane reactor where you can directly convert carbon dioxide to ethylene. So currently I'm working on that, for example. You can convert carbon dioxide from the atmosphere where you can produce ethylene or ethanol, for example. You can produce ethanol, or you can also produce methanol and so on. Some chemical compounds that are useful from the carbon dioxide from the atmosphere. So there are different emerging applications that are really interesting, and yeah, I'm also happy that I will discuss this later so that it will be of interest for you to work in this area, like splitting the water to produce hydrogen with ion exchange membranes, and also converting carbon dioxide into some useful material like fuel chemicals or fuels like ethylene, methanol, and so on. Which are used in our daily life, no, for energy production and so on. So we will discuss this in our hopefully in the next lecture if we have a possibility. Yeah.
For Marlene, is there any feedback or is it quite clear for you? Okay, Dr. Ramato, this is one more question from Alfonsina again. Yeah. What is the state of the art for the scalability and stability of the ion exchange membrane of water electrolysis for H2 production? Is it ready to be industrialized or under research?
Okay, so I think I can see the question here also. So the question is related to the state-of-the-art membranes, scalability and stability of the ion exchange membranes for water electrolysis. Is it already under industrialized conditions? So yeah, it's a good question, and also, in fact, I didn't discuss much about this in my today's lecture, but hopefully I will do this in our next continuing lectures. But in order to answer this question, of course, there are industrial technologies for production of hydrogen from water by ion exchange membrane technologies. For example, the alkaline electrolysis. There are different industries that use alkaline electrolysis technologies to produce hydrogen. But okay, to be clear, these technologies, the alkaline water electrolysis technologies, in fact, they are using different type of membranes, not the ones that I mentioned to you, like the ion exchange membranes. They use a kind of porous membranes, which are diaphragm. So now there is an extensive research going on in order to replace this diaphragm with the ion exchange membranes. So that is a very hot topic now currently in this field. But still there are industrial large-scale production of hydrogen by water electrolysis by using these diaphragm materials in the case of alkaline electrolysis. We have PEM technology. The PEM technology is quite limited because in the PEM you use proton conducting membranes, which are really expensive. Also, you use a very expensive catalyst to make hydrogen in the case of acidic water electrolysis or PEM, polymer electrolyte membrane water electrolysis. Those are quite expensive technologies because you are using platinum and iridium, which are really expensive catalysts to deploy in industrial scale, and that's why we have the cheaper way of producing hydrogen or alkaline electrolysis, which I mentioned to you, because it's working in alkaline environment. You don't need expensive catalysts like platinum and iridium. You can simply use cheap earth abundant catalysts like nickel, and with a simple porous diaphragm that allows you to separate the electrodes, and you can make water electrolysis. So the ion exchange membranes, the scalability is determined. The scalability is a very important factor when you make new membranes. There are membranes that are produced in industrial scales. There are industries that supply to us membranes, for example, the Fujifilm or Fumatech that I told you before, Neosafety. And so there are companies which are providing you membranes, which can also provide you membranes in large scale. So the question is the main question is the scalability. The main concern now is the scalability of the high performing membranes that we make. Some high performing membranes that we make are not scalable because the method of production is very expensive, very complicated. Some okay. So the stability is also a problem is a major problem. It's a major problem. Is the stability, for example, in the alkaline electrolysis for hydrogen production. It's a major problem, which is still requires a new knowledge. So and without addressing this, there is not membrane that is now scaled and used in industry, which is really stable and meeting the required fulfillment. As I told you, in industries, they are using diaphragm materials. The diaphragms are not, they are membranes, but they are not kind of ion exchange membranes. They are a kind of porous membranes. They transport ions, of course, but they have a little bit different structure from the ion exchange membranes that I talked today. So it is very important to understand that the ion exchange membranes that are really very stable are not 100% in the market. Well, it's still an under development or I would not say like in the coming decades, 2-3 decades to reach the industrialized applications. So the stability and also the conductivity, not only stability, but also conductivity are the key major issues that need to be improved and also provide the membranes into industrial scale. I think we will I will give more detailed discussion on this in the next part, and also by looking in how the technologies for hydrogen production and also the carbon dioxide reduction to works with ion exchange membranes. It's better to discuss in detail in our next lectures.
Thank you, Dr. Ramato. Okay. Maybe last questions. Is there any question from the participant? Okay, Nurul Fadila, please, you can ask the question.
Good afternoon, Dr. Ramanto. I'm Nurul Fadila from Bioproses Engineering. I want to ask you about effect of types backbone in membrane. Do various types of backbone affect the performance of membrane, or is just affect the physical characteristic of membrane? Thank you.
Okay, if I understand your question very well, thank you for your question. I think you said the different type of membranes, the various types of membranes will affect the performance, you said. Can you please elaborate a little bit your question?
May I elaborate the
Yeah,
question? Yeah.
a little bit, yeah.
The type of membrane's backbone. Is there any
Backbone, okay.
Yeah, the
okay.
backbone. It just
Okay.
affect the physical characteristic, or is
Yeah.
also affect the performance of membrane. Yeah.
Oh, yeah. Okay, yeah. Okay, perfect. So the backbone. So the question is about the backbone. So the backbone, you have seen here, is a good question. So the backbone of the backbone is just what I was just shown you before. So the backbone is a very important part of the membrane. In fact, it's also one important part of the membrane. When we talk about ion exchange membranes, we are always focusing on the fixed charge groups. All right, you can see here. Okay, let me just. So you can see here, this one is the functional group, the side chain, and the backbone. I can simply say the properties, the stability, and that I was talking previously, showing you in the diagram on the mechanical properties and so on, the perm selectivity, the resistance, and all these properties are in fact influenced by all of this, I would say. Especially how you order the functional group, the side chain, the backbone, and so on. How you can order them on one another. So here I'm showing you two examples, okay? Where you have the side chain, where you put the functional groups either on the backbone, or you can put the functional group on the side chain. These are two different materials, and the performance is completely different. And the backbone here looks similar, right? So it is blue and blue. Here it seems the backbone looks like the same. If you change this backbone to a different polymer, you are in fact, depending on the type of polymer you put, in fact you will change slightly at least one of the properties of the membrane. It can be the perm selectivity, the resistance, the conductivity, or whatever you like. But I will not say to you that the changing the backbone is really going to affect the key membrane properties like the perm selectivity and the resistance. So for people working in our field, we are very much interested with the conductivity and the stability, or the perm selectivity, and also this kind of properties. I will not, in the first instance, I'm not going to tell you, okay, change the backbone or change this kind of thing and so on. But the main focus will be the functional group. That is the first thing that you need to know, because the functional group is the one which is really affecting these properties extensively. However, the backbone is also very important to some extent, because depending on the structure of the backbone and the side chain, you are going to influence, for example, the conductivity of the membrane. Because, for example, if you use the blocopolymer, there are backbones that now we use in our lab, which are called blocopolymers, because the blocopolymers allows you to easily manipulate the interstitial channels. So you can change, you can choose different blocopolymer type of membranes, and you can change the interstitial channel structures easily, and that will allow you to tune the transport of the ions. Of course, you can do that. But blocopolymers, and if you also use another type of polymer, then the conductivity and so on is going to completely change. However, we will not say directly, okay, this base material is also very good for stability as well. It is very important also to control the stability of the membrane, because the base materials, for example, I work with SPIC, sulfonated polyether ketone. SPIC membranes. So the SPIC, sulfonated polyether ketones, are very well studied in fuel cell, for example, and they are known, this kind of backbones are known to be very stable, mechanically stable and conductive, and also heat resistant. All right, so if you use some other type of polymers like PPO or others, maybe they are not very well stable as SPIC membranes. So the backbone, of course, is very important, but the functional group will be really very important. For example, if you talk to me in terms of hydrogen production, because the functional groups, if they are not stable, they are just they are the ones which are easily affected by the external environment of the operation and so on. So the functional group is really very important. And then, of course, the backbone and this side chain, the reinforcement, the cross-linking, and all these things are also very important. So, as I told you, the first step is to choose the backbone. It can be SPIC, sulfonated polyether ketone, or PPO, polypropylene, PVDF, all different kind of backbones that you have. Of course, you need to choose that, but then the functional group is also the key aspect of the ion exchange membranes.
Okay, Mbak Nurul Fadila, is it clear?
Very clear, Bu. Thank you for your answer, Dr. Ramato.
Okay. Okay. Thank you very much for Dr. Ramato. Before we end this session today, I would like to summarize a little bit about the guest lecture. So this lecture has explained about the fundamental of ion exchange membrane. The first thing is the types of membrane is homogeneous, heterogeneous membrane, and then the structure of the membrane, and the we have matrix, we have backbone, we have a functional group in the ion exchange membrane, and the properties of the ion exchange membrane like perm selectivity, ion capacity, and the perm and the charge density. Yeah, so Dr. Ramato has clearly explained how to those properties has been linked to each other, yeah, and how they correlate to each other. So thank you very much, Dr. Ramato and all the participants. Before I close the session, please, we invite you to a photo group session, yeah. So all the participants, please turn the camera on. Okay, we will wait you around a minute for open your camera. Okay, maybe we can take the picture for the first slide. Yeah, is smile. 1, 2, 3, smile. Okay, and for the next slide, 1, 2, 3, smile. And the last slide, smile. Okay, thank you very much. And we, in the end of the guest lecture today, on behalf from the organizing committee, we extend very much appreciation for Dr. Ramato for delivering a great guest lecture and all the participants today. Thank you and good afternoon and have a great day and see you for the next guest lecture.
Thank you.
Yeah. Thank you very much. Thank you very much all.
Thank you.
Thank you. Thank you. Bye. Thank you.
Terima kasih Bapak Ibu dan Mbak Mas kalian. Terima kasih Bapak Ibu sekalian.
Ya,
Dan
makasih Bu Igit.
Mas Mbak sekalian ya. Terima kasih. Saya izin live, nggih.
Nggih.